Module 4, Section 9.1, Trigonometric Identities and Equations. First we want to identify the fundamental identities. The reciprocal identities are that cotangent of theta is 1 over tangent, secant of theta is 1 over cosine, and cosecant is 1 over sine. And the reverse is true. Tangent is 1 over cotangent, cosine is 1 over secant, and sine is 1 over cosecant. We have the quotient identities, which state that tangent is sine over cosine, and cotangent is the reciprocal, cosine over sine. Then there's some new identities, the Pythagorean identities. Sine squared plus cosine squared equals 1. That's our first one. Tangent squared plus 1 equals secant squared. And then 1 plus cotangent squared equals cosecant squared. So that we can see these are separated. Then we have our negative number identities, and this has to do with whether or not we are dealing with odd or even functions. So we see that sine of negative theta equals negative sine, and the same is true for its reciprocal, and this is due to the fact that sine is an odd function. It's simply the definition of being odd. Cosine of negative theta equals positive cosine of theta, and the same is true for its reciprocal function, and this is due to the fact that cosine is an even function. And then tangent of negative theta equals negative tangent of theta, and the same is true for cotangent, its reciprocal, which also displays that tangent and cotangent are both odd functions. So the only two functions that are even are cosine and secant. The rest are going to be odd and have this definition. It will be necessary to recognize alternative forms of the identities above, such as the fact that sine squared of theta is simply 1 minus cosine squared, or cosine squared is 1 minus sine squared. All that's happening is we're taking our first Pythagorean identity and solving it for one of our trig functions. Looking ahead to calculus, you're going to need to be able to work with identities to simplify an expression with the appropriate trigonometric substitutions. And this is just one example. If we say that x is 3 tangent of theta, and we want to evaluate this function substituting 3 tangent of theta in for x, then we will have the square root of 9 plus 3 tangent of theta, quantity squared. Now recall from algebra, when you have two things being multiplied, raised to a power, both of them will receive that power. So we end up with the square root of 9 plus, now 3 squared, and then tangent of theta squared. So that is the square root of 9 plus 9 and then tangent squared of theta. Now I do want to point this out. It doesn't matter what our trig function is. We'll just use tangent in this case. When you square it or raise it to any exponent, writing it this way is identical to writing it this way. And so you'll see us go between the two. Now from this step here, we can factor out a 9. So we have the square root of 9 times 1 plus the tangent squared of theta. And remember, when we're multiplying, we could split that up and say that it's the square root of 9 times the square root of 1 plus tangent of theta, tangent squared of theta. So the square root of 9 is 3, and then we have the square root of 1 plus tangent squared of theta. Now, put another star here. Remember that we have that the tangent squared of theta plus 1 is equal to secant squared of theta, and that's one of our Pythagorean identities. So we're going to substitute secant squared in here in our square root formula. So we have 3 square root of secant squared of theta. Now in the first quadrant, or in our interval from 0 to pi over 2, the value of secant is positive, so we will have that the square root of 9 plus x squared is then equal to 3 secant of theta. And we've eliminated our square root. And let's take note that this is for all values of theta between 0 and pi over 2, since that's the interval that secant is positive. Now let's look at expressing one function in terms of another. We want to express the cosine of x in terms of tangent of x. Since the secant of x is related to both tangent of x and cosine of x by identities, we'll use those. So we know that the cosine of x is equal to 1 over the secant of x. Now we also know that secant squared of x is equal to 1 plus tangent squared of x. So let's find a way to put the two together. If we take the square root of both sides here, we'll have that the secant of x is equal to plus or minus the square root of 1 plus tangent squared of x. So we'll substitute this expression over here for secant of x. So we end up with the cosine of x is equal to, our plus or minus will pull out, and we have 1 over the square root of 1 plus tangent squared of x. So what we'll do is we will multiply the top and the bottom by 1 plus tangent squared of x in order to eliminate the square root in our denominator, or rationalize our denominator. And so we will get plus or minus now the square root of 1 plus tangent squared of x over just 1 plus tangent squared of x. So we've now defined a cosine of x strictly in terms of tangent. We'll choose the plus or the minus sign depending on what quadrant we're told x is in. Now let's look at rewriting an expression in terms of sine and cosine. We want to write tangent of theta plus cotangent of theta in terms of sine theta and cosine theta. So we'll take tangent plus cotangent and use the quotient identities, knowing that tangent of theta is the sine over the cosine, and then the cotangent would be the reciprocal, or the cosine over the sine. Now we want to put these two fractions together in one fraction, so we need to get a common denominator, and that will be cosine times sine. So we need to multiply here the top and the bottom by sine, and here we'll multiply the top and the bottom by cosine. And this gives us our common denominator of sine and cosine multiplied. So we will have sine squared of theta plus cosine squared of theta here. And this is our Pythagorean identity. Remember that sine squared plus cosine squared is equal to 1. And we substitute that. So we have 1 over sine theta cosine theta. So we've now written tangent plus cotangent in terms of sine and cosine. Just some rules to follow when you're verifying identities. The very first thing is you must learn the fundamental identities. You need to have them memorized. You're going to encounter them often and you need to know each and every one. Secondly, you want to try to rewrite the more complicated side of the equation so that it is identical to the simpler side. Thirdly, it is often helpful to express all functions in terms of sine and cosine and then simplify the result. Next, usually any factoring or indicated algebraic operations should be performed. For example, when we have here sine squared plus 2 sine theta plus 1, you need to be able to factor that as sine of theta plus 1 quantity squared. So you need to kind of recall all your factoring from previous algebra courses. Also here, if we want to put these two together as we did in a previous example, finding a common denominator and combining and adding fractions. Number 5, as you select substitutions, keep in mind the side you are not changing because it represents your goal. And lastly, if an expression contains 1 plus sine of x, then multiplying both the numerator and denominator by 1 minus sine of x would give you 1 minus sine squared of x, which could then be replaced with the cosine squared of x. And so any kind of combination of that would work. And these are just some ideas as you approach each problem on how to do them. So let's look at some examples. We're going to look at verifying identity when we're working with only one side at a time. So we want to verify the following identity, that the cotangent of x plus 1 is equal to cosecant of x times cosine of x plus sine of x. So we want to work with the more complicated side, and that's going to be the right side. So we'll work with it first. Okay, remember that cosecant of x, the reciprocal, is 1 over the sine of x. And we're multiplying that by now cosine of x plus the sine of x. So when we put this together, we have cosine of x plus sine of x over sine of x. Now, since we have these multiplied over one denominator, we can split it up over our common denominator as cosine over sine plus sine over sine. Now recall that the cosine over sine is simply our definition of the cotangent of x using the quotient identities. And then anytime we divide something by itself, it's simply 1. So we've now verified our equation. And we know that we have an identity since the left side equals the right side. Now let's look at what we could do with a calculator. We want to graph our two functions in the same window, letting y1 be our left side. And remember, on our calculator we don't have a button for cotangent, so we'll let it be 1 over tangent plus 1, and y2 be our right side, cosecant times cosine plus sine. But since we don't have a button for cosecant, we use the fact that it's 1 over sine, and we'll put this function in. So let me pull up our calculator where I've already graphed these. Here we have our functions in our calculator. And we want to set our window to be negative 2 pi, and all you have to do is type in negative 2 second and our up key and hit enter, and it'll change it to our decimal. So we're from negative 2 pi to 2 pi, and we're going by pi over 2 as our scale, and our y values will be negative 4 to 4 with a scale of 1. Now when we look at the graph, you see that we have these lines connecting it. Here we've graphed it and we don't have those lines. Remember that this is in dot mode, so let's go back to our calculator. Go to your y equals screen and arrow back to the beginning and hit enter until you get to the dot mode, which is just 3 dots. So it's your very last one. Now we'll hit graph, and you should see that we have the same picture. Now we want to look at our table, and I'll pull up our table on the calculator. It should look similar to this, so we press second and graph to see our table, and it gives us values for x and then both of our equations, y1 and y2. And you should see that they're matching up since they're identical and the graphs were the same. But notice here we have an error for this value, pi over 2, in y1, and we don't have an error in y2. Remember that comes from the fact that we had to use 1 over tangent in terms for cotangent. To verify an identity, we must provide an analytic argument. You have to do it by hand. A graph can only support but not prove an identity. So this is just one way to show that you have an identity. You'll still need to be able to do it by hand. We want to verify that the following equation is an identity. Now when we look at this, we see that our left-hand side is more complicated, so that's the side that we'll work with. Tangent of t minus cotangent of t over sine of t cosine of t. And remember that our goal is to show that it's equal to secant squared of t minus cosecant squared of t. So let's split this up. We have the tangent of t over sine of t cosine of t minus the cotangent of t over sine of t cosine of t. So now we'll change to sines and cosines. The tangent is sine over cosine. And the cotangent is cosine over sine. So we want to simplify this. We have the sine of t over the cosine of t, and instead of dividing by sine cosine, we'll multiply by 1 over sine of t cosine of t. And we'll do the same on our other side here. So we see that now we can cancel our sine here, and over here we can cancel cosine. So we end up with 1 over cosine squared of t minus 1 over sine squared of t. But remember that 1 over cosine is secant, so we now have secant squared of t. And 1 over sine is cosecant, so we have cosecant squared of t. So there we have shown that the left side is equal to the right side. Now let's do another example, and this one I want to show how we need to use our algebra. We'll work with our left-hand side here, cosine of x over 1 minus the sine of x, and we want to show that it's equal to 1 plus sine over cosine. So what we'll do is we'll multiply the top and the bottom by 1 plus sine of x. So when we do that, we end up with the cosine of x times 1 plus sine of x over, in the bottom we'll have 1 minus sine squared of x when you do this multiplication and simplify. Now remember that 1 minus sine squared of x is our Pythagorean identity, and we'll get cosine squared of x. And our numerator is still cosine of x times 1 plus sine of x. Now we can cancel cosine with one of our cosines in the bottom. So we have 1 plus sine of x over cosine of x. And so we've shown that the left side equals the right side and verified our identity. Now let's look at verifying identity when we want to work with both sides. We want to show that this equation is an identity. So the first thing we're going to do is work with our left side to reduce it to a simpler form. And to do that, we are going to change to sines and cosines. Remember that secant is 1 over cosine of alpha plus tangent is sine over cosine. And we'll work with our denominator the same way. Now, because we have the same denominator in the numerator here, we can put this together and we'll have 1 plus sine of alpha over cosine of alpha divided by 1 minus sine of alpha over cosine of alpha. Now, since we have a fraction divided by another fraction, we change this instead of using division, and we have 1 plus sine of alpha over cosine multiplied by the reciprocal of our bottom fraction. So we have multiplied by cosine of alpha over 1 minus sine of alpha. So now our cosines will cancel, and we end up with a simpler expression of 1 plus sine of alpha over 1 minus sine of alpha. Now, bearing that in mind, let's now look at the right side of our equation, and we want to work with it. So looking at our numerator, we see that we can simplify this or factor it down to be 1 plus sine of alpha quantity squared divided by the cosine squared of alpha. Now, cosine squared is the same as 1 minus sine squared. And 1 minus sine squared, if we factor this as the difference of squares, then we'll have 1 plus sine of alpha times 1 minus sine of alpha. And our numerator is still 1 plus sine of alpha quantity squared. So what we're then able to do is to cancel one of our groups here with 1 in the top, and we end up with 1 plus sine of alpha over 1 minus sine of alpha. So we've shown that our left-hand side is equal to this quantity and our right-hand side. And that's another way we can verify our identity, by showing that both sides are equal to a common term. Now let's look at an application. Tuners in radios select a radio station by adjusting the frequency. These tuners may contain an inductor L and a capacitor C. The energy stored in the inductor at time t is given by the following equation. L of t equals k sine squared of 2 pi ft. And the energy stored in the capacitor is given by C of t equals k cosine squared of 2 pi ft, where f is the frequency of the radio station and k is a constant. The total energy E in the circuit is given by E equals L plus C. We want to show that E is a constant function. So, to show that it's constant, we're going to use the two equations for our inductor and capacitor and our total energy equation, and we'll put these together. So we know that L was k sine squared of 2 pi ft, and C was k cosine squared of 2 pi ft. So what we'll do is we'll factor out a k out of both, and we'll end up with sine squared of 2 pi ft plus cosine squared of 2 pi ft. Now take note that we will have that 2 pi ft is representing our angle here. So we have k times sine squared plus cosine squared of our angle, and sine squared plus cosine squared is simply 1 using our Pythagorean identity. So we show then that E of t is equal to our constant k, which is what we were asked to show.